Let's try this problem number 38 of your textbook. The problem says that there is a uniform chain of mass M and length L overhanging a table with two-third part on the table. That means there is a table, yes, and there is a chain like this, and two-thirds of the chain is on the table, and its total mass is m. So obviously this mass is m by 3, and this mass is 2m by 3. The question is, when the work done to pull the whole chain on the table, I have added this part by pulling it from the other end. That means you pull it from the other end gradually and put the whole chain on the table. Now the problem of this problem is initially there is a length of the chain here. So the work done to pull it up depends upon mass of this length. But the moment you pull up a slight portion, at the next moment or the next installment, the mass is less because some part has been pulled out. So work done also will be less. So we have sorts of differential or integral equation equality actually. So here you find that mass per unit length is equal to m upon L. Right? Now you consider that initially x length is hanging. And then you consider a small dx part is pulled up. Let us consider x length is hanging. So mass of hanging part is equal to x by L. So weight of the hanging part, weight force, weight of the hanging part mg by L into x. Now let us consider a very small length, dx is pulled up. If a very small length dx is pulled up, then what done to this very small length tw, that means an infinitely small amount of work is equal to this force acting downward, mg x by L, that means mg by L into x multiplied by the displacement cost, which is dx. Write it down here again so that it is easily visible. Mg by L into x into dx. Therefore, total work done or done W is equal to integration M by Lx. Integration limit is initially the total length which was lying down here was L by 3, and finally it will be 0. So work done will be the bring it to make the value of x. The value of x will be from work done from 0 to L by 3. This is equal to mg by L comes on outside because it's not a function of dx. It's not a function of x into integration of x is x square by integration of x is x square by 2. That limit from 0 to L by 3. Again, this 2 you can take outside. So mg by 2L, mg by 2L, and this limit is from this limit when x is equal to L by 3, this is L square by 9 minus, when it is 0, then all function is 0. So this is 0. This is equal to mg L square divided by 2 into, this is 9, 2 into 9, 18. So this is the total work done to pull the chain upwards. Okay? Now what we shall do, we shall go to the next problem. We shall take this problem and this problem is problem number 39. We'll do it today because it's a similar, very similar problem. It says that once again, there is a chain, uniform chain of mass capital M and length capital M. Overhangs a horizontal table with 2/3 of the part on the table. So the situation is set. Here is a table. Here is a table, and here is a chain. And 2/3 of the chain is on the table, 1/3 is below the table. So this length is given L. So L by 3 part is hanging, and 2L by 3 part is below the table. Now, problem given is the friction coefficient between the table and the chain is mu. Now there is a friction. In earlier problem, there was no talk about any friction. Find the work done by the friction during the period the chain slips off the table. That means it says that friction is so small that the chain by itself slips off the table. And here, mind it, if the chain slips off the table, then work done is by the chain against the friction. But the paper setter asked you to find out the work done by the friction. That means whatever work done by the chain and negative of that will be the answer. Negative of that will be the answer, right? Now, find out once again, like in earlier problem, the mass per unit length, mass per unit M by L. That case, what is the reaction? Reaction of the part, reaction of the part on the table for unit length M is equal to M by L multiplied by G, multiplied by G. And therefore, the frictional force Fs is equal to mu M G by L, right? And if similar, like in earlier question, if we consider that x length lying on the table, if lying on the table, then Fs is equal to mu m g upon L multiplied by x. Now, if dx part slips down, now dx length slips down, then work done by the chain, work done by the chain is this force multiplied by dx. So we can designate is a small amount of work dw. It is equal to mu mg by, here it is capital L actually, and m is also capital M, mu capital mg dx. That case, so total work done is total work done, W is equal to integration of mu mg by capital X dx, and integration is limit. Integration will be on x, and value of x goes from L by 3, 0 to 2L by. This is equal to mu mg capital L, these are all constants. Mu m capital L, these are all constants. Integration of x dx is x square by 2, and its limit is 0 to 2L by 3, right? So now if this 2 also is a constant, we can take it out. So it is mu mg upon 2L multiplied by, now this will be x square So x square, x value, we have first value will be 12 by 3 whole square. Second value will be 0. So we do not write, avoid writing the second value. Is equal to mu capital M G by 2L that multiplied by 4L square by 9. This is equal to 2 and 4 makes 2 here. So this is equal to 2 mg L. This L and L square also only on L will remain 2 mu mgl divided by 9. Now, this work is done by the gravity. So let me put it here in a different color. This work is done by gravity. So, work done by friction is negative of that is equal to minus 2 mg L by 9. And this will be the answer. Okay. So in our next session, we shall take other problems.